Thank you very much for inviting me to this conference. I would like to give you my own personal experience of I use Open Science Grid to help my research in trying to simulating heavy ion collisions. So my primary interest is to study matter in some extreme conditions, mostly as the particle related to particle accelerators, where experiments do collision of nuclei with very high energies. So my personal interest is trying to develop computational framework which can simulate what happens in these collisions, illustrated at the right-hand side of the cartoon. As you can see that after the two nuclei collide with each other, the system will go through different stages and emitted a lot of particles at these red points here. So basically, all my simulations are done like this way, and this is one of the visualization we make from the numerical package. So we really want to understand is basically what actually matter behave under very extreme conditions, namely very high temperature or very high densities. So we collide two nuclei with very large velocities near speed of light, and system will go through a few different phases indicated here. So the most interesting phase we will look at will be so-called Quark-Gluon Plasma phase, in short QGP, where systems lives in the form of quarks and gluons, which are fundamental building blocks of our visible matter. However, in the experiments, this dynamics happens very fast. It's only happened in a few times 10 to 23 seconds. So this is called yoctosecond physics, which is far more faster than any detector can detect or response, which only react in a nanosecond scale. So in order trying to interpret what the experiment measure at the end about the property of matter at the very early stage require us to develop numerical framework, which actually can rewind what is measured at the detector to this early phase, and then help us to understand the property of these matters at these extreme conditions. So one of the things you can see is that from experiments, there's a lot of challenges trying to compete with experiments. So this is an event display from one of the detector at the Large Hadron Collider. This is one of the lead-lead collisions, which convert enormous amount of collision energies into new matters, which is kind of like you think about evolution from Einstein's equation. You basically convert energy into new mass of the new matters. So what it does is we collide heavy ion collisions. One collision will actually produce tens of thousands of particles, which is recorded in these tracks in the detectors. And these collisions are done actually with about tens of millions of events per second at this Large Hadron Collider. And each of these collisions produce about thousands of particles. So it's actually a tremendous computing challenge from a theory side to actually compete with those statistics, because in the theory, when we want to simulate such an event, it takes about a day to finish, to simulate one event. And we want to build up similar statistics compared to the experiments and trying to compare with the data in there. So this is actually really a big computing challenge in our field. So what would we want to understand these type of matters, because we want to look at how these matter behave collectively as a group. So as in our daily life, we will find that there's many of these emergent phenomena when you have many particles together. For example, if you look at the flying pattern of a school of bird on the sky, each of the bird will not know this global structure, but however, if you look at as the system as a whole, you will see different emergent patterns show up. And this also applies to a school of fish, or even you look at a bicycle race, you will see kind of a collective behavior in this way. So in nuclear physics, this Quark-Gluon Plasma is a many-body system, and it is actually exhibiting really fascinating behavior or fascinating properties in nature. So the Quark-Gluon Plasma, in short, is actually the hottest and smallest and most perfect fluid in nature, which means that actually carries the lowest specific shear viscosities compared to regular fluid like the waters or even cold atom or helium which is also with very small viscosities. But you can see that this cartoon shows that the value of the viscosity in Quark-Gluon plasma is about a factor of 2 or factor of 5 or smaller than all the ordinary fluid. And lately, also this fluid also carry very large angular momentum when it collides two nuclei with each other, so which means that the vorticity, or like a local rotation of the fluid, is actually enormous. And this is actually also the most vertical fluid in nature. As a physicist, what we like to understand is how this emergent phenomenon happens when we consider about the fundamental interaction with particles in this case. So as a whole in the community, what we actually want to establish is basically trying to quantify the properties of this hot, dense fluid using experimental data. So under this box, I list a few properties that you would expect from a liquid. For example, the speed of sound in this liquid, how large it is compared to, say, the speed of sound in water. And also what's the viscosity values as a function of temperature, and also other variables here. And there's also different other transport properties of fluid that as a physicist would like to understand. On the right-hand side is sort of the experimental observables that can be measured in experiments. So in the ideal case, what we'd like to see is that we have a one-to-one mapping, so certain property of the fluid can be measured or constrained by certain variables in the experimental measurements. So in this way, we can actually measure all these things and try to constrain all these properties. But in the reality, it's not that case, because all these different properties will have small or minor effects on other observables. So that it's a very complex network trying to invert what is measured in experiments back into the properties of these heavy ion collisions. And this inversion really requires us to build up theoretical framework trying to actually map those properties into the experiments, and then also do the reverse mapping from the experiments. So this is basically what I'm usually working on, was basically develop a numerical framework which can simulate different stages of the heavy ion evolutions as its function of time for many events, and then average the simulation observables and compare with the experimental data. So this is just a cartoon that's showing that there's actually different stages of building blocks in this framework that we use, and we basically simulate from the left to the right as we combine different stages of the code together, and then simulate one event as a whole, and then eventually we'll compare with experiments. So this is the task we like to do, is to actually basically set up this numerical framework on the open science grid and try to run it with the advantage of the resource in the open science grid. So there are a few concerns that on the computing side. So first is we have decent library dependence depending on different modules in the codes. And also the whole package, if we want to compile, take about 30 minutes to compile on a single CPU. So with these concerns, so we decide to actually use a Docker or Singularity container, such that the package can be portable to many different platforms easily. And also using the container, we can pre-compile the code inside there, so that we don't need to recompile the code every time we run it. So second is that I want to give you a rough idea how our job size and job duration run on the open science grid. For a single CPUs, our one job event take about 2 GB of memory and 1 GB of disks usage. So we have 2 running modes to simulate events. There's a computational cheap way, which is called 2+1D simulations, where we reduce the dimension into 2-dimensional space and 1-dimensional time. So usually this simulation, one event take about 5 hours to finish. So those events actually are ideal to run on OSG, because that we don't get much large penalties from restart our jobs. Most of the jobs can be run effectively in a single runs. There's more precise or more ambitious runs with 3+1D simulations, where we have 3-dimensional space in the simulations. And you can see this actually increased the simulation time by order of magnitude. And this actually is a challenging time actually on OSG, because in this type of time, we actually need to concerning about the job may not be run very efficient. And this is also what we found at the initial time that we just deploy these 3D runs to OSG, and the performance is not very great. So what we found is that we want to actually either just request a multi-thread jobs, we request all 2 or 3 CPUs to actually run the jobs, or we can actually implement self-checkpoint, actually, which efficiently make the simulation more efficient. So, so this actually deploying to the Docker environment also changed our daily life kind of code development style to more streamlined, similar to industry level. So basically, our local kind of development, we use it to upload to GitHub, and we use the GitHub Actions to automatically do continuous integrations and distributions to Docker Hub to build up the Docker Hub image. And then on the open science script, we use Singularity Pool to actually pull down the latest version of our own Docker image to the public directories, and then launch our job with that. So as you can see that this IEBE-Music on Docker Hub is already have more than 100,000 downloads. Most of them actually is coming from OSG, while we are actually trying out these kind of routines. And we have another kind of a similar setup for another framework, which was already getting about more than 1,000 downloads. So now let me talk a little bit more detail on the self-checking point in our case. So because in our code is actually a multi-stage approach, it is actually natural to actually set up breaking points at the end of every stage of the simulation, indicated at this yellow dash line here. So what we do is in our Python script, which is a driver to drive the whole simulation flows, we basically first set up the checkpoint to basically store all the output of the simulations up to a certain stage into a checkpoint files. And then at every stage, we can actually unzip these files when we restart this simulation at a later time. So we set the restarting time for the checkpoint to be about 12 hours, so that we can actually run at least 1 or 2 stages of these multi-stage evolutions, and then restart the simulation from there. An outcome from this is that we found a few things that practically that is useful to know when we run this self-checking point mode. One is that the disk space requirement may be increased slightly because we have the intermediate tar file that we actually need to store while we run the simulations. So it is actually quite useful to request twice of the disk space usually used for your normal run. So this twice will be a safe bet if we just blindly use the checkpoint. And we found also during the simulations, the checkpoint used the disk space in your home directories as a buffer, so that at some point, if you run many jobs together, you want to monitor your quota, whether it will be kind of exceed your disk quota or something in the home directories. And the benefits of having this self-checkpoint is that we found that almost 99% of these 3D simulations can be finished within 3 days, which is significantly increased the efficiency compared to the brute force runs we did before, which would take more than 4 or 5 days to finish with similar amount of levels. So here is basically the group. So the performance in my group. So we actually used Open Science quite a lot. So you can see that within the last 3 months, we already consumed about 7 million CPU hours in total, and we use quite efficiently over time as a user from Open Science Grid. And last but not least, I can also show you that with our group, we have recently published 4 papers using the Open Science Grid resource. One of them is already published in the Physics Review Letter, which is the most prestigious journal in our field. And we are also in my group, we are training young students, even high school and undergrad students, to use the Open Science Grid resource to do scientific computing. So that's all I have. Thank you for your attention.
right, thank you, Chun. Any questions from the audience? And again, all of our science speakers this afternoon will be joining us in our discussion session too. I see applause from some people. And to ask a question, you can drop it in the chat or use the reactions feature in your Zoom window to raise your hand. So Chun, I've got a question. How many students total in your group?
So right now we have, I have 2 postdocs, 1 grad student, and 3 undergrad, and also 2 high school students. So not all of them are in my group list because some of them are using local resource to do some small scale calculations. But I'm more and more drawing them to Open Science Grid because the setup is way more easier compared to local setup because of these Docker implementations.
All right, I've got another question that came straight to me. I don't know if that person wants to repeat it in the chat for everybody, but it's asking, is the code all in Python?
No, so actually the code, most of the heavy computing part is in C++. I use Python mostly for connecting those code together. Yeah. So the glue between all these code are done by Python, but individual blocks are done by C++ mostly.
And are you compiling those to static binaries?
Yeah.
On OSG?
Yeah.
Interesting, thank you. All right, well, thank Chun again and have him join us later in the discussion session.